I was confused. I had set my alarm thing during orientation, and it said that it was at 11:30, and then my alarm thing didn't go off because I didn't set it right. I was like super worried that I missed it.
Well, you didn't, but other people are missing the session right now. Yeah, so our session will be at 1:30. And then actually, I'll just tell you now, we're not going to have a session next week.
All right.
I am going to be we're doing like a staff team building all day. So we're going to be at Dave & Buster's, I think, or something like that. So we're not going to have a virtual session next week, but then usually we will have them.
Okay.
At 1:30.
Now concludes our lockout drill.
Okay.
You may now go about your business. Thank you for participating in the lockout drill.
Okay. On to the real stuff. All right, so we're going to just go through this kind of quickly since it's just us two. I'm going to record, so people who are tuning in and missed the session will lose out on some bonus point opportunities as well as the DBA opportunity. So they'll have to make those things up. So today we're going to define molarity, solve molarity problems using stoichiometry and given information from a word problem, and then complete the Module 5 DBA. So you came here starting in second semester, so how familiar are you with moles and what a mole is and how to calculate moles? Did you get to that in your other chemistry class yet?
We kind of did. Sorry, kind of just did labs. That was it.
Oh, okay. So you might have calculated in the lab. So we're going to review how to find moles and like what that means, but then also this new term, molarity. So what is molarity? Which, by the way, all of these PowerPoints get posted, but it might benefit you to write things down, especially if you've already done this lesson. It's good to go back and kind of add stuff in because I will go over shortcuts. I love shortcuts. So anytime there's a shortcut, I'll tell you. So molarity is represented by a capital M, and that might seem not that important, but it is because a lowercase m is mass, right? So when you see a lowercase m, you're looking at mass. When you see a big M, you're looking at molarity, right? Which is going to be a big difference. So the capitalization of it is important. It is a unit of concentration expressed in moles of solute per liters of solution, or per 1 liter of solution. So what that means is we want to know how many moles of a substance are dissolved in 1 liter of solution, which is usually water. Not always, but usually. Sometimes it's like an acid or something else. So basically what we're looking at is the molar quantity, but in a solution form. It's really easy to calculate. If you know your moles and your liters, then you just do moles divided by liters, right? But if you don't know those things, it can get a little bit more complex. So in simplest terms, how do we find moles again? Because that's going to be an important step to finding molarity, knowing the moles. This is sort of what the questions will look like for this type of assignment. 110 grams of NaCl are dissolved in 5,000 milliliters of water. What is the molarity? Right, so that's the kind of question that you'll see here, and you think, oh, okay, I got to find moles and liters and divide. Well, first we need to find our moles of our solute, and solute means what's dissolved, or the solid. So in this case, it's NaCl, or table salt, right, sodium chloride. So our solute is sodium chloride because it's getting dissolved in the water, and we need to know our moles. Well, we're given grams. Usually you'll be given grams. Why? Because in a lab setting, which I'm sure you're familiar with, most of the time you're measuring mass or volume of something to add it, right? Rarely will you see add 1 mole of sodium chloride, right? You'll see add 110 grams. Okay, so let's find out how many moles that is. In order to find our moles, we need to know our molar mass, which we get from the periodic table. So to find molar mass, you look up the mass of each element and add them up, depending on how many of each one there are. So in this case, we take sodium which conveniently I'm sitting right next to a periodic table. I'm not just looking off into space because I don't have sodium memorized. Sodium is 22.9 or 23 grams per mole. That's the unit that we use to describe the molar mass. Again, all I'm doing is looking at the mass on the periodic table. So 23 grams per mole is for sodium, and chlorine is 35.45. 35.45 grams per mole is chlorine. So we have 1 sodium and 1 chlorine for each of these molecules. So all we're going to do is add these two numbers together, which is where I got this 58.4 grams per mole. So the way that I set up stoichiometry is I do it in these tables just because it's the easiest way to show online. And each one of these tables will be representing multiplication. So right here, what I'm saying is that we're multiplying this column by this column by this column. In this case, I think that actually is the equals, so never mind about that one. Okay, so anyways, please feel free to stop me if you have any questions. So back to what we're trying to do here, find the moles of our sodium chloride. So we start with the given from the problem. We have 110 grams of sodium chloride, and we want to know, okay, how many moles is that? Well, we're just going to multiply by our conversion, our molar mass that we just found. So our molar mass is 58.4 grams of sodium chloride per 1 mole. And this may be something that you remember or not, but moles are actually 6.022 times 10 to the 23 atoms. So 1 mole is equal to that many atoms. So really, mole is just a fancy way of saying a group of atoms. That may seem like an arbitrary number. It was determined in a laboratory, right? For each mole of a substance, that's how many atoms are inside. So that's another conversion factor that we could potentially need to use. In this case, we're not dealing with atoms, just moles, so we're good to go. So we do this simple division here, 110 divided by 58.4, and we end up getting 1.88 moles of sodium chloride. Hi, Vitali, glad that you are here. So we know our moles now. That's honestly the hardest step of molarity, is you might have to convert to moles. These are both things that we covered in first semester. So if you need extra support on them, Ethan, feel free to let me know, and I can link you to some older virtual sessions too. If you want to see more about practicing calculating moles, molar mass, that kind of stuff, because we've sort of been doing that. I hit them right in the beginning with that because it's hard. Okay, so we have our moles. And Vitaly, I think you've already done this quiz, so you're going to be an expert on how to do these problems, hopefully. Okay, next step is our solvent, or in this case, water, in liters. Very important. It has to be in liters, not milliliters. So we need to be able to convert between milliliters. You might even see grams per cubic centimeter and have to convert to milliliters and then to liters. That would be kind of a weird situation, but you might see that. So a very helpful conversion to just have memorized at this point is that 1 liter is 1,000 milliliters. And, or you could also think of it as 0.001 liters equals 1 milliliter. So both of those are viable ways to convert here. You could also Google it if you need to as a last resort to check your work. But knowing how to convert between metrics will make your life a lot easier if you stay in math and science. So learn it now. All right, so how do we convert to liters? Well, I already set it up down here, but we know that we have 5,000 milliliters. We know that there are 1,000 milliliters in 1 liter. Vitaly, yes, you can. You're actually, well, we're going to do the dBA at the end. So if you want, maybe you just want to turn my volume down and kind of tune back in probably like 10 or 15 minutes, and then you can do the DBA. Or actually, I can just give you the link now. Look at that, so accommodating. Okay, we're gonna fast forward to the DBA really quick so that I can give Vitalia this link. And then everybody else will get to that in a second, so no worries about getting into the link right now. But Vitalia is gonna go ahead and do that, and you'll be our model with questions there. Okay, so, oh good. Finally on the right page again. So in this case, we need to multiply by our conversion factor between milliliters and liters so that we can get into liters. Because again, the only rules for molarity are that you need moles and liters. And anything can be converted into moles. Liters is a little harder, but in this case, they'll usually give you milliliters, so it's a pretty easy one. So we're gonna do 5,000 times 1 over 1,000, or 5,000 divided by 1,000, and we get 5 liters of water. So in that case, we have our moles, we have our liters. What do we do to put these two things together? We divide. Pretty easy. Honestly, this is some of the easier math that we're gonna have in the class. So just keep that in mind. Why can't I move this? I hate Zoom sometimes. You guys can never see my Zoom struggles, but I have like, it makes you have these headings and you can't hide them, and then it won't let you move things, and it drives me nuts. Okay, that isn't working. Oh, that moves. Okay, yay, I figured it out. Okay, of course you guys don't see any of that, so to you, you're like, what are you doing? I'm just reorganizing my screen, it's okay. All right, so it's a mess in here. Anyways, now we find our molarity, which again is moles divided by liter. So we found we had 1.88 moles of sodium chloride. We found that we had 5 liters of water. So we do 1.88 divided by 5, and then we get 0.376 molarity, which again is a capital M because it is different than mass, right? And if you see that capital M, that should already tell you this is a solution. This is how many moles are dissolved in a liter of this solution. So I could rewrite this as 0.376 moles per 1 liter because they are in fact the same. So keep that in mind. If you need to use molarity to then convert to other things, right, that's what molarity is. It's moles per liter, which I'm going to say 15 more times so that it stays in your mind forever. So that's the basics of finding this. Now, of course, most questions are not going to be that easy. They're not going to give you moles and liters, or, you know, they'll make you work for it a little bit. But this is more of the type of question that you'll see in the class. So, how many milliliters of a 2.5 molar hydrochloric acid solution would be needed to react completely with 32 grams of magnesium metal? And then they'll give you an equation, right? So this is more along the lines of what you're going to see. It kind of should seem similar to a limiting reactant problem. Why? Because we want to know how much of something is going to be needed to react completely with this amount of magnesium metal. So in other words, magnesium metal is kind of our limiting reactant here because we only have 32 grams of magnesium metal, and we want to know, well, how much of this hydrochloric acid solution are we going to need in order for all of the metal to react? Okay, there's a lot happening in this, so let's break it down. First part, what does molar solution or molarity mean? It means moles per liter. So we can write that as 2.5 moles of hydrochloric acid to 1 liter. Pretty easy. We want to start with the magnesium. That seems kind of counterintuitive because you're probably thinking, yeah, but we're trying to figure out the hydrochloric acid. Well, yeah, but the metal is limiting us. So I'm going to go through this. I'll probably say it a few times. You guys let me know if you want me to say it more than I say it. Let's see, because we also, oh good, Oliver, you're here too. Okay. So first step, we have 32 grams of magnesium. Oh, thank you, Oliver. I will fix that because it should not require permission, but I think I didn't set it on edit anyways. So good thing that you're saying something now. We'll fix that. Okay, it should work now. Thank you. Again, interrupting me is always an option here. So we're going to start with the magnesium because we know how much magnesium we have. We can have as much hydrochloric acid as we need. Again, we're in grams here. Grams are not going to help us. We don't know what 32 grams of magnesium means, right? We don't know how much we're going to need to react. We need moles. So again, we're going to get the molar mass from our periodic table of magnesium. Magnesium's mass is 24.305, right, which I rounded here to 24.31. Again, we know that's grams per mole. So what am I doing here? I'm basically converting our mass of magnesium into moles. So 32 divided by 24.31 will give us how many moles of magnesium we have. Then this part will seem like limiting reactant. We're going to then look at the molar ratios given in the equation. Because again, we need a balanced equation. Always, all of your equations should always be balanced. Why would you work with an unbalanced one? You wouldn't. So in this case, we come up and we see that for every 1 mole of magnesium, we need 2 moles of hydrochloric acid for this equation to happen. So that's where we get this ratio. For every mole of magnesium, we need 2 moles of hydrochloric acid. Just look at the coefficients in the equation, right? If they were both 1, they didn't have anything in front of them, then this would just be a 1-to-1 ratio. You would still write it in the question because you want to practice knowing that that's where you get that coefficient from, is from the equation, and that's actually telling you how many moles you need of hydrochloric acid. Okay, now we know our molar concentration, right? But again, that's moles dissolved in liters. So we need to somehow incorporate that into this. Well, remember what I always say about units. We want our units to cancel. So far, we're doing pretty good. Grams magnesium is canceling out with grams magnesium. Moles magnesium canceling out with moles magnesium. Moles hydrochloric acid. Well, we're going to need to cancel moles of hydrochloric acid out. Well, guess what? We know that we have 2.5 moles per 1 liter of our HCl solution. So we can actually take that information from the question and finally start plugging it in here. That will allow us to cancel out moles of HCl. And now we're just in liters. Okay, that seems good, except what did they ask us for? Of course, milliliters. Right? So we're not done. We have to convert to milliliters, which again, that's why I said that's an important one to write down. 1,000 milliliters in a liter. Now we're able to cancel out liters, and we're left with milliliters of HCl as our only unit left. Well, is that what we want? Yeah. How many milliliters of a 2.5 molar hydrochloric acid solution? Okay, well, this is going to tell us that if we do all the math. So do the math with me because I want you to make sure that you can do it. So you will, once you get your calculator open, because it takes me forever to do that, do 32 divided by 24.31 times 2 divided by 2.5 times 1,000. Should give you the answer here. So again, when you're multiplying on one of these long stoichiometry type equations, right, you just multiply all the things on the top and you divide by all the things on the bottom. You can do it in any order. Like I did top, bottom, top, bottom, top, bottom. You could do all the ones on the top, then all the ones on the bottom. It really doesn't matter. You're going to get the same number because it's the same math. So how much did you get if you do all that math? 32 divided by 24.3 times 2 divided by 2.5 times 1,000. What did you guys get? And by the way, Ethan, we use that a lot. So if you see the chat, it usually lights up like orange to tell you that someone's typed in it. You can always have that open and you can type questions in there, especially if I'm talking. Or you could type math numbers in there that you get by multiplying and dividing all these answers, which no one's talking to me, so I'm very concerned. But I got 1,053. Oh, you're trying to use calculator. Good. Keep trying. So I got 1,053 milliliters, which it seems silly that they would have asked us for milliliters because they might as well have said 1.05 liters, right? But hey, what can you do? So again, to summarize, when you're given a question like this, they're going to tell you which reactant you have a certain amount of. You're going to try to figure out how much of the other one you need. That means you're going to need to use both, right? You need not only the magnesium that they told you how much you have, but you're also going to need your molarity or your moles of your hydrochloric acid, as well as the coefficients from your full balanced equation. So we're going to try one more. But again, your answer should be 1,053 milliliters HCl solution. Okay. When in doubt, make your units cancel. That's really the trick here. Okay, let's try one more example. So, how many grams of iron metal do you expect to be produced when 215 grams of a 65% by mass iron 2 nitrate solution reacts with excess aluminum metal? That's a lot, right? Now we're introducing this other concept, which is percent by mass. Again, I'm going to go through this kind of quickly. Definitely look through the lesson because they have more examples of this to practice it. But again, this is a common thing that you would see. Why would something only be 65% by mass? And what does that mean, right? Well, we're going to figure it out right now. So a 65% by mass solution means that there are 65 grams of iron dissolved in 100 grams of the solution itself. A big symbol for these, AQ, an aqueous or aqueous solution, however you want to say it. It means it's a solution. It's dissolved in water. So if you're saying 65% by mass, what that means is that you scooped out 65 grams of iron 2 nitrate, dumped it in some water, stirred it up. And not just some water, but you dumped it in 100 grams of solution, right? And we know that grams are not exactly the same as milliliters, but it's very similar to molarity. We're talking about how the solution was made, essentially, is what they're telling you. Because you could have an 85% by mass solution, you could have a 100% by mass solution. So really, they have to tell you this because solutions can be made in whatever way you want to make them. Okay, so that's what the 65% by mass solution means. This is what I would do every single time. I would write out grams of iron 2 nitrate to or over 100 grams of iron 2 nitrate solution. Again, I would just double check that my equation was balanced, right? Usually if you already see coefficients, it's a pretty good sign that it is. However, just make sure 3 irons, 2 aluminums, 2 aluminums. All right, we look good. All right, so you can also multiply your starting amount of iron 2 nitrate by 0.65, in other words, finding 65% to find out how much of it is in the solution, right? Because they're telling us that there's 65 grams per 100 grams of solution. Well, we're being told that we have 215 grams of solution. So we want to know, well, how much of that's the iron 2 nitrate? we're going to take 65% of it, right? Or multiply by 0.65. By doing that, we find out that we have 139.75 grams of iron 2 nitrate. Again, 65% mass solution means that it is 65 grams of the solid per 100 grams of solution. If we're starting with more than 100 grams of solution, which in this case we are 215 grams, we have to find out what 65% of that is. So again, you would just type into your calculator 215 times 0.65, and that will give you 139.75. That's the shortcut way to take a percent, right? You multiply by the percent as a decimal. Okay, that was a lot, and we haven't even started the question yet, but that's what all the percent by mass stuff means. Again, guys, think about percents. Percents always add up to 100. Right? 65% of something means that there was 100. It's, 100 would be the max. Now, of course, you can have percents over 100, right? In chemistry, we don't have that. That's like some economic statistic stuff. In chemistry, you cannot have more than 100% of something in a solution. There's no way. Okay, so now we have our starting amount of our iron 2 nitrate in solution, which I write in solution. You could just write AQ. You could also just not write that because you know that we're talking about a solution. That's fine. Now we need to go into moles, right? Because again, we're still in grams here. That's semi-helpful, but not really. We need to know about moles. So now we have to find the molar mass of iron 2 nitrate, which I have conveniently done for you, right? But how would we do that? Well, we would add up all of these things. We would add up iron, which is pretty heavy once I find it, 55.845. Nitrogen, which is 14. We need 2 nitrogens, right? Because there's 2 nitrate molecules. And then we need 6 oxygens, which oxygen is 16. So you would do 16 times 6 plus nitrogen times 2 plus iron. That's how you get 179.3. Again, this is a molar mass, so this is grams per mole. Great, we're already well on our way to eliminating grams from our units. Cool, we're in moles. Everyone's happy we're in moles. Now we need to know, what are we even looking for, right? Because we probably lost sight of that at this point because we did so much already. Well, we want to know how many grams of iron metal are produced. So this time we're actually looking for a product. We're looking for this guy right here. Iron, the solid. In terms of our reactants, we know that we're starting with 139.75 grams of our iron 2 nitrate. And aluminum is in excess. That means we can use as much as we could possibly ever need to use, right? So we would just keep adding aluminum for as long as we need. So really, we don't even need to care about aluminum. It is unnecessary in this equation in terms of solving it. What we do need, though, is those ratios, which we get from our balanced equation. For every 3 moles of iron 2 nitrate, we produce 3 moles of iron. Makes sense, does not always work out that way, right? Which is great, because then we have a 3 moles of iron to 3 moles of iron 2 nitrate. Are we done? No, because we want to know grams. This will tell us moles, which is a step in the right direction, but we need to know the grams of iron that are produced. So what do? We find the molar mass of iron, 55.85. Yep. Grams per 1 mole of iron, that's going to cancel out all of our units except for grams of iron, which is exactly what we want. How many grams of iron metal do you expect to be produced? Iron, our product, is happening to be appearing in the same amount of moles as one of our reactants. So now we do the math. So I'm going to do mine a little bit differently this time. Let's see. 139.75 times 3 times 55.85 divided by 179.3 divided by 3. And you should get, say again, please. Certainly will. 139.75. Really, it would be times 1, but we don't need to put that in the calculator. Times 3 times 55.85. Sorry, what's wrong, Logan? Oh, your screen is about a minute behind. That's weird. I don't know what to tell you, Logan. That might be your internet. Or it could be my internet, which I can't really do anything about because I'm at the school, which should be the greatest internet. But I'll plug my computer in, maybe that'll help. Sorry, Ethan, I got distracted by reading the chat. But, oh, that's really weird, Logan. Is anyone else experiencing that? When I'm crossing something out, it's not happening until like a few seconds or a minute later? Okay, that sounds like it's just you. Logan, try to log out and come back in. See if that helps you. Sometimes Zoom just needs like a little, adjustment. Back to what we multiplied. 139.75 times 1 times 3 times 55.85 divided by 179.3 divided by 3 divided by 1. And what do you get if you do all that stuff? I got 43.5. Is that what other people are getting? Yep, 43.53. Excellent. And again, what is that though, right? Because that's not our full answer. Grams. To be extra nice, you could write iron. But that is what, okay, good, Logan. I'm glad that worked. So that is how we figured out how many grams to use when we're talking about equations that have aqueous solutions, right? Because this is pretty realistic to real chemistry. In fact, a lot of times you'll have to make those solutions, right? They'll say you need a, 85% by mass solution of this, and you have to make it. Could also be that you don't have that solution, but you have another one, so you might have to adjust it so that it's correct for what you need, right? So a lot of things don't react as well if they're not dissolved in water. And why would that be? Why would we need to dissolve something in water? Why would we even need to make a solution? Like, what's happening to this iron 2 nitrate when it's in a solution? What's happening to it? A new chemical, that's a good guess. Sorry, I was responding to a text. Okay. Well, what's happening? Yeah, I'm not sure is a perfect thing to say. It's becoming ions, right? Why would we ever put anything in water? Because it dissolves and becomes ions. So now that iron is a positive ion, that nitrate is a negative ion, now those ions are free to interact, right? Whereas if this was bonded as a solid, it might react under certain situations, but until we break it into ions, right, nothing's going to happen. So anytime something's in a solution, you should immediately think ions. That means those molecules are now charged. They're floating around in water. They're able to interact. So that's the whole purpose of making a solution. Because I guarantee if this was not aqueous and it was just solid iron 2 nitrate and you mixed it with solid aluminum, guess what? You have a pile of metal, but nothing's going to happen, right? They're not going to interact with each other. However, you put it in a solution, aluminum will replace iron and iron will be left by itself. That's a big difference, right? So you need solutions for ions to be able to touch each other essentially and interact, which is why we care about molarity and percent by mass and all of these types of things, because again, you want to have a solution where it's all ions, right? You don't want to put too much where there's just metal floating around at the bottom because it didn't really dissolve. And you also don't want to put such a tiny amount that it doesn't do anything. So this is all kind of finding out the amount that you would need for reactions to happen. Okay, so if we had to summarize what we would do here in terms of this process, so using molarity in problems, right? First step is identify what they give you, right? Or look at the givens. Look at what are you looking for? Convert to moles. Doesn't matter what problem you're doing, you're probably going to have to be in moles. So just do it, go to moles, right? How do we do that? We use molar mass from the periodic table. I'm going to go to the next slide. I think it's more blank so that you guys can see this better. Oh, it's not really that much more blank. This one kind of is. Oh, no, it won't let me write in there. Okay, well, I'll have to make a new chart now. So convert to moles, right? Use the coefficients from the balanced equation to solve. I'll just say that. But those are the main steps. What are you looking for? What are you given? Convert to moles. Use the coefficients from the balanced equation to solve. The only difference would be if it's a percent by mass solution, right? Because then you might have to figure out how much mass you're dealing with. Again, though, for a percent by mass, all you need to do is multiply move that stuff out of the way. All you need to do is multiply the percent by whatever amount you're starting with, right? In this case, that's in grams. Pretty rarely will they just straight up give you moles. It happens occasionally. Because again, mole means something, but in reality, if I said, get me a mole, right, you're going to say like an animal? Like, I don't know. Because in terms of like math and numbers, right, we don't really view it as 6.022 times 10 to the 23 atoms, because what does that even look like, right? Is that like what I'm holding in the air? Like, who knows? So grams are much easier for us to understand and visualize and touch, right? But moles are still important. All right, so now you're going to try. So let me move these instructions over here to the corner. All right, how many grams of chlorine gas are needed to react with 3.5 liters of course, this thing's right in the way, of a 1.7 molar potassium bromide solution? Okay, well, I see that we're being given molar, no percent by mass, so that's good. I don't have to worry about that. We're given the number of liters we have of a type of molar solution. Oh no, I left my answers on here from last year. So you guys are getting a cheat right now because I'm about to erase it. So write down what you can while I erase it so we can do it together. Okay. Oops. Okay. What are we going to do here? I don't remember how many of these I need, but we'll do 4. Okay. So let's look at what we're given. We're given 3.5 liters of a 1.7 molar potassium bromide solution. Okay, we're also given an equation. We want to know the number of grams, or the amount of grams of chlorine as a gas. Doesn't seem necessarily like, oh, I need to write that down, right? But think about it, chlorine could be dissolved in a solution, right? Because chlorine can be ions. So in its gas form, it's not an ion, it's bonded to itself. So basically, we're being told how much potassium bromide we have, and we need to figure out how much chlorine gas you need to react with the full amount here, which is 3.5 liters. So let's see what we know so far. We know we have 3.5 liters of potassium bromide solution. Cool. What can we multiply by next? What does this molar mean again, right? What could we write that as? Additionally, it's 1.7 molar or 1.7 moles per liter. So I see some suggestions. Multiply by 1.7 moles. Yes, Ethan says the same thing. Yeah, right, because what else are we going to multiply with? We have no other numbers, right? So it's definitely those. You guys are right. We want to cancel liters out, so we'll put liters on the bottom. And we know that for every liter, we have 1.7 moles of potassium bromide. And again, how do we know that? They told us in the question. All we had to know was what the definition of molarity or molar is, and we go, oh, that means 1.7 moles per 1 liter. Well, that's cool. Now our liters are canceling out. We're in moles. Okay. Well, what do we need to find here? We want to find chlorine gas. How many moles of chlorine gas will we get if we have 2 moles or however many moles of potassium bromide, right? They have a 1-to-2 relationship here. So for every 2 moles of potassium bromide, we get 1 mole of chlorine gas. And how do I know that? Right, I'm looking at my coefficients from my balanced equation. Chlorine just is in a ratio of 1-to-2 for our potassium bromide. So now, just a quick check of our units, what's canceled here, right? We've gotten rid of liters. We've gotten rid of moles. We're in moles of chlorine, however, we don't want to be there. We want grams of chlorine as a gas. Seems counterintuitive to measure gas in grams, but you do it. So how do we get from moles of chlorine to grams? What would we multiply by? Or what would we need to look up? Avocado's number. Close. Avogadro. Mass, yes, molar mass. Right? So we know for 1 mole of chlorine, we just look at the mass on the periodic table. However, do we? Chlorine gas is Cl2, right? It's 2 chlorines bonded together. So my molar mass of chlorine gas is going to be 35.45 times 2 because there's 2 molecules. Okay, 45, or no, wait, am I saying that? 35.45 times 2. So chlorine gas has a molar mass of 70.9 grams per 1 mole Cl2, right? Because this is a chlorine gas. Okay, probably should write the 2 on this too. So now all our moles will cancel, and we're left with grams. And that's what we want. And we're left with grams of chlorine. I should write the Cl there. Cl2. So now we just do the multiplying. We do 3.5 times 1.7 times 70.9. And we divide that by 2. And we get a lot. We get 2,109.275 grams of chlorine gas, or Cl2. Now that seems like a lot, but if you really think about it, if we're given 3.5 liters, think about a liter. A liter is quite big. So you're given a ton of potassium bromide solution here. It would make sense that you would produce or need that much chlorine gas for this to happen. So it does kind of make sense, right? Because usually you would not be working with 3.5 liters of solution unless you were trying to produce like a lot of product. Like maybe you were trying to produce potassium chloride for something, right? Usually you'll work with much smaller numbers. In fact, usually it will be less than a mole, less than a liter kind of thing. So that may seem insane, like, whoa, 2,000 grams. Yeah, I mean, that's kind of a lot, right? But really, when you look at how much other reactant you have, it makes sense. Okay, so your best bet on these equations is to look at all the examples again, set your stuff up just like the examples, and most importantly, make your units cancel out, right? That's what's going to get you to the answer. Oh, I have liters. What do I know that I can cancel out with liters, right? Write down all the numbers they give you. And again, make sure that you understand that 1 mole, like if we have 0.35 molarity, that's the same thing as 0.35 moles per 1 liter. Those are in fact the same thing, right? Molarity may not be able to cancel out as easily. Moles per liter, you can definitely cancel. So keep that in mind as you go through these types of problems. Okay. I was going to do another one, but we're going to run out of time if we do that to have time to do the DBA. So maybe we'll do that in the next virtual session, which, by the way, a lot of you guys were not here in the beginning when I announced we're not having a virtual session next week because we're going to be doing a staff development thing. So next week we will not have one. But oh, yeah, sorry. It's probably because I rounded my mass. So that's a great question, Logan. It's because I rounded it. So yeah, you're right. We'll be slightly off. 66.9 is the more accurate molar mass. I just did 35 times 2, or 35.5 times 2. Yeah, so mine was rounded. Yeah, which is why rounding is bad. There you go. No, I don't care if you round. As long as you're in the ballpark and you understand how to do the math, that's what's most important. So for the DBAs for this class, right, most of you have probably already clicked on the link. Just in case you didn't, though, here's the link. DBAs are really easy. It's just a way for you to make sure that you've mastered the 3 most important things from the module or the unit, right, which are defined by me. In this case, these are the 3 most important things from the modular unit. So if you feel like you know these 3 things, then you did a really great job in this module. What you're going to do is when you're ready, which could be now, or it could be later today or whatever, you're going to write your name, and then underneath each question, you write your answer. And we do it all in one document like this so that you can see what other people say too, right? So if you're not sure, maybe somebody else in the class puts it in a way that you go, oh yeah, I remember what that is. So the first question is, what is the difference between a compound and a mixture? How does a solution differ from a mixture? That one's kind of a trick question because really solutions are mixtures, right? So be able to explain how and why not every mixture is a solution. What is molarity, which I said a million times today, clearly important. And then how do you calculate molarity? Why would you need to dilute something or add water to it? Again, something that we just talked about, hint, hint, ions, right? So those are the 3 questions for the DBA. You can go ahead and take a second now. I'm typing the code word into the chat, which is ironic because it's something that I said pretty recently. That code word will get you 5 bonus points on your molarity quiz. So you can add it as a comment. You can email me and say, here's my code word. Can I get my, bonus points? However you want to do it, I don't care. But write that down so that you have it and you know that those are your bonus points for attending today's session, right? Sometimes we have bonus points. Sometimes we will have exit tickets. Sometimes we'll have other things. In this case, you get 5 bonus points just for coming and hopefully learning something about molarity. Does anyone have a question about any of the stuff that we just went over, or about the class, or about what you're supposed to turn in, or what you're supposed to be doing right now? Okay, I'll take it from the silence that you don't. Well, you can always email me, right? So if you think of a question later or you're doing a molarity problem and you're like, what's happening in this question? Just send me an email. All right, so otherwise, I will not see you guys next week. I'll send out a reminder that the session's canceled, but I'll see you in 2 weeks. and we will be in module 6 at that point. All right, so thank you for being here, and I will see you guys next week. How many people are in the class? That's a good question. I think 15 or so. But we have at least 7 people who work or have a reason why they can't attend the virtual sessions. So about half the class has excused stuff happening, but usually we get probably like 5 or 6 people in these. So hopefully we'll get a few more people next week. But yeah, otherwise it's a pretty small class. It's less than a regular class for sure. Okay, so I'll see you in 2 weeks. Email me if you get stuck on anything.